just that. Okay, refer to model answer, analyze where did you go wrong. I need question paper to be able to help you. Okay, where did we stop last class? Do we have exams for other students? We were doing the mechanical rates. Mechanical energy. Waves. Mechanical waves, okay. Sound waves. Okay. So we discussed all the terms associated with wave. Amplitude. No, amplitude, no. Frequency, wavelength, not yet. We had started. What have we started? Like the examples of model examples of mechanical wave. Okay. Propagation of sound. Did we complete that? Compression, rarefaction. Formation of compression and rarefaction. No. Have we covered propagation of wave? Sound propagates with the medium when forming a series of compression. Okay, so we have done that. So we have propagation of sound wave. So basically, how does it propagates? Let's say you have a listener over here. So initially, when there is no sound, right, the air molecules will be uniform. But when the this is how sound propagates, right? So basically, what do you require for propagation of sound? First is you require source of sound. Source of sound in this case is tuning fork. Then you have medium for propagation. Medium for propagation. Okay, which is air in this case. And this is detector. So detector in this case is listener. Listener. Okay. So what happens is when the tuning fork moves forward, it compresses the air molecule. So basically, let's say each air molecule will undergo oscillation about its mean position, like this. So it will disturb the next. Okay. So turn by turn, all the air molecules will be disturbed. And finally, the air molecule will disturb the eardrum. So that's how the disturbance passes from air molecule to air molecule. So when the tuning fork comes forward, there will be compression. Okay. So when it goes back, the air molecules will now spread apart. When it leans forward, air molecules will compress. So compression and spreading. So this is called compression and rarefaction. So this is how sound actually propagates through the medium. So how does it propagate? It propagates by transferring the disturbance. Okay. Sound propagation takes place by transferring the disturbance. This we did last class also. From air molecule to air molecule. Which during which a series of compression and rarefaction are formed. Okay. So this is how sound propagation takes place. So basically, compressions are the region of high pressure and high density, right? Compression or region with high pressure and density. Whereas low pressure. So this is the mode by which sound propagation takes place. So the disturbance, what is the direction of propagation of disturbance in this direction? So V the speed with which the wave or the disturbance travels. Disturbance means wave. This disturbance is itself is called wave. So disturbance is passed from molecule to molecule. Okay. And what else happens during sound propagation? The particle of the medium oscillates at its mean pitch. It does not travel, does not leave its position. So these are the key points that should be covered when you are answering propagation of sound. During propagation of sound, the particle of the medium oscillates at its mean position. So this is the key. It does not leave its position. Okay. So this kind of propagation where the particle oscillates parallel to the propagation of sound, propagation of wave, that kind of waves are called what kind of wave? Huh? Mechanical. Mechanical, so any wave which requires medium is called mechanical wave. It is longitudinal. Sound, yes, longitudinal. Okay. So let us now see what are the types of waves. Did we cover this? Did we cover this? So there are two types of waves, mechanical is correct. No.
C and E.
Mechanical, right? Mechanical waves. What is mechanical waves? Requires medium. So within mechanical also we have two types. One is longitudinal and the other is transverse. Within mechanical wave also you have two types of waves. So example of longitudinal wave is here the particle oscillate parallel to the propagation of wave. Okay, like sound wave. Here, particle of the medium. Oscillate parallel to the motion of okay. Here's particle oscillate parallel and the disturbance is transferred horizontally. So what is the example here? In this case, particle oscillates perpendicular like this, while the wave motion is lateral. Particle move up and down. Here particle move laterally or horizontally. So what is the example here? Water waves on the free surface. So water molecule oscillates up and down. Free surface water waves. Right? Then you have vibrating strings. So vibrating strings of musical instruments. Isn't it? And the string is plucked. How do you get the wave motion? Up and down. But the vibration travels along the string. The second type of wave is electromagnetic wave.
It does not need a medium.
It does not require medium. It can travel in vacuum. That's how sunlight reaches Earth, right? So most of the distance traveled by sunlight is in free space.
So light is also wave.
Yes. Light is electro.
Wave is an energy.
Wave is an energy. Like I said, wave is the medium of propagation of energy. So during when one particle collides with other, what does it do? It transfers its energy, kinetic and potential.
There are there any medical for this sample?
Yes. There are simple ones. Second type of wave is electromagnetic waves. इसका example है light. light waves, radio waves. Yeah, infrared, all that. These are example of electromagnetic waves. But electromagnetic wave also has transverse nature. This is what EM waves have transverse nature. So what is oscillating perpendicular to the propagation of light wave?
Perpendicular. So
Transverse means something should be vibrating perpendicular to the direction.
it's 90 degree to the direction.
Yes, so this is perpendicular. So this is 90. Correct? Here it is parallel. So you should write here in transverse when particles, in this case, the particles of the medium oscillate perpendicular to the wave motion. Okay, so it oscillates perpendicular to the direction of wave motion. Now in light, you don't require material medium. So here, what is oscillating? The particles of the mediums are oscillating, and the energy is transferred through them. But in light wave, how it is traveling through space? So that's a different thing. It's a thing that will come to in 12th standard. So basically, it is electric and magnetic field. So suppose the light wave is coming towards you like this. Okay. So electric field and magnetic field, they oscillate perpendicular to the direction of propagation. And they themselves are also perpendicular to each other. So all three, the propagation, the electric and magnetic field, they are all three mutually perpendicular. And you will learn when electric field generates magnetic field and magnetic field generates electric field. That's how they regenerate each other. That's why they don't require medium. They generate, so they are self-sustaining. Electric is sustaining magnetic, magnetic is sustaining electric. That's why it is called electromagnetic waves. Okay.
So electromagnetic wave only have transfer.
Yes. So the electric field is 90 degree. Let's say that the light is coming towards you like this. So you have electric field in this direction and magnetic field in this. Understood? So it's like and magnetic field will be here. So these are different planes. One is in this plane, the other one is in this. Understood? So there is 90 degree between electric and magnetic field. Okay. And the direction, this direction also is 90 degree. This is the light. Clear? This is how it comes. These are the two planes. Like the electric field is here. Imagine that floor, that corner of the floor, that wall and the floor. This is how it is. Understood? That wall and this floor. So in that wall you have electric field, in the floor you have magnetic field. And propagation is the line running the floor and the wall. Anyway, you don't need the details of this, okay? Okay, so what is electromagnetic waves? No medium is required. No medium is required for EM waves. Okay, and I told you what is the transverse nature. It is due to electric and magnetic field. E is electric field, B is magnetic field. Okay. So anyway, so we are going to only learn about sound wave in this time, which is mechanical wave of longitudinal type. Even in mechanical wave, you have transverse. Okay, because water waves require medium. What is the medium here? Water itself. So water molecules are oscillating up and down at their main position. Like if you're standing near a pond still, okay, you drop a stone. What do you observe? The ripple will spread in circles. But is the water flowing? No. Water is oscillating at its position. Just the disturbance, the energy. Okay, the energy is flowing ahead. So when the energy is flowing, what is it doing? It is disturbing the water molecules at other positions. That's how it is going. So are we good till here? Then just to demonstrate that sound requires a medium to travel, you have this bell jar experiment. What is this bell jar experiment? Let's see. Bell jar experiment. Bell jar experiment proves that sound requires medium for propagation. Proves the necessity of medium for sound wave propagation. Okay, so basically, what do you have? You have a bell jar like this. It's like a glass vessel with no base, like a bell. Okay, no base. So this thing is open. So where it is kept? It is kept on a let's say rubber floor or something like that. Okay, so it's like a hard rubber floor. Here you have actually suspended an electric bell. What you have is an electric bell, and here you have a hammer. So when the hammer actually hits the gong, you will hear the sound. Okay. Now this bell is suspended inside the jar, and the electrical connection is provided to it. Okay. So when the switch is pressed, then the bell will begin to ring. Now let us say there is a listener here. Yeah, some listener is here. So basically, what happens when the bell rings? What will happen? When the sound is produced,
Air particle will disturb.
air particle here will be. Did I covered in the last class? So the air particle will be disturbed. That will disturb the wall of the bell. It will also disturb the wall. That will disturb outside air. Okay. So in this case, sound will be heard by the observer or listener. Okay. So when there is air, initially you will hear the sound. Now what is done is a vacuum pump is connected. There is a vacuum pump. So now when the bell is pressed, bell is ringing, right? Bell is ringing, and also the vacuum pump is started. So what will happen when the bell is ringing and the vacuum pump is started? The air
There is no air to yours.
will be sucked out.
Since there is no air particle,
So air, no sound is getting produced.
but there is no air particles.
You carry the disturbance.
Yes.
So
Air particles will oscillate and the sound.
so what happens as the air reduces, the sound heard by him reduces also. And when the air is completely sucked out, then he sees that the bell is ringing. He can see that the bell is ringing. Let's say the hammer is on this side. So he can see the motion of the hammer. But he will now stop hearing the sound. Okay? So this proves that sound requires medium for propagation. Bell is ringing as usual. But now when there is vacuum, he does not hear it. So first is listener hears sound. Of that. Then air is present. Listener does not hear sound. Then air is sucked down by vacuum pump. Okay, although you can see that well is ringing. So it sees the ringing. So light is traveling, right? Because light does not require medium. So he is able to see the ringing of the bell. But sound is now not reaching it. Okay. So what you have fitted here is the bell is mounted with the help of a cord. Okay. Next. So how do we represent a wave? Representation of a wave. First of all, you can draw this diagram. So any wave can be represented like this. Okay. So y-axis could be pressure, density, or displacement. X is displacement. So in transverse wave, this will represent vertical oscillation, transverse wave, right? For longitudinal wave, this will represent compression, maximum pressure and maximum density. And this will represent least density, least pressure. Okay. Okay. So this thing is also called as amplitude A minus A. Okay. It is the maximum displacement of the particle of the medium from its mean position during wave motion. That's the characteristic property. We'll come to it. First, you understand what is amplitude. See, amplitude is this. This is dot is the mean position. What is dot? Mean position. During wave motion, it will be compressed. So this is plus A, maximum displacement on one side of the mean position, then this will be minus A. Equal displacement on both sides. Here it will be plus A above, and this will be minus A. So in this situation, it will form a compression at the position where it is having maximum displacement. It will form compression.
Minimum displacement.
It will form rare fraction. Yes. Understood? So
So
for
the minimum distance is when it compresses the most.
what is minimum distance? Minimum distance is mean position. Zero distance. When it is not oscillating, it will rest at its. See, this is the oscillation, right? Right now it is rest position. Now when I set it into vibration, this is the maximum displacement. This is amplitude. Okay, now the amplitude is reducing with time. And every time it is crossing the mean position. So what is oscillation? One complete to and fro motion. Therefore, oscillation begins from here. To, fro. Forward, backward motion is called one oscillation.
So when is compression is at the highest point.
When the particle of the medium come closer. So they are doing like
And then
this.
after pushing it to the next particle, when they expand, when they come back to their third.
We have grown in this. Whom is the now we have propagation of sound. Just watch this video.
Teenagers are building businesses with AI, while the only AI you know is Chat GPT. Let's be real. In our previous video, we studied that sound needs a medium for propagation. This, it requires some medium to travel from one place to another. But how does it really travel through the medium? What happens to the particles of the medium? Let us find out. We now know that sound is produced by vibration. When the object is vibrating, it sets the particles of the medium around into vibration. In the process, the nearest particles to the source
This is compression.
from the mean or equilibrium position. They start to collide with the particles adjacent to them.
And then this will come further.
These particles then also
Now
get
this is
then
compression.
lead to the
Compression has moved forward. This is
You're doing
gone.
fabulous different, but
And it is receding.
that sound features are here.
Clear.
We see that this creates some disturbance flowing through the mean.
During motion, each particle is oscillating at its position, but by the sheer dynamism, some of them come closer, that's compression.
That's what that is.
And when they spread out, that's when rareness. So these are high pressure, high density and low pressure, low density region. But if you just focus on compression, okay, then you will see compression is moving forward. Just focus on one compression here.
Here, the way that sound travels through the medium. We see that portions of the medium are not traveling through the
And
source.
likewise, rarefaction also. Rarefaction also is there.
Used by a source which is traveling in the medium. Particles are merely oscillating from their mean positions. This disturbance created by the vibrating object in the medium is what we call a sound wave.
So the disturbance is energy based.
Let us study this with the help of a tuning fork. Here we take air as a medium of propagation. Here we have a tuning fork made up of steel. This shows the initial condition of the air particles of the medium when
When no sound wave, when it is not vibrating, all particles are evenly distributed.
not vibrating. When we strike its prong on a rubber band, we start hearing a sound. How does the sound travel through the medium? The two prongs of tuning fork are vibrating. Let us concentrate on motion of one of the prongs first. Say the one on the right. When it's away from its mean position, it pushes and compresses the air particles around it. This creates a high pressure region, also called compression. This compression travels in the medium as a disturbance. Here the density is high. That is, the particles are very close to each other. When the prong comes towards its mean position, the pressure on the right decreases, sound decreasing further.
Like this,
Sound continues its motion towards left.
this disturbance will not stop
It's
here.
a low pressure region, but the fault has rarefaction. We see that at this point, the compression in the form of disturbance has reached this region. This rarefaction also travels in the medium as a disturbance. Here the density of particles is less. This, the particles are far away from each other. As it continues to vibrate, we get a series of these compressions and rarefactions. This continuous sequence of compressions and rarefactions is what we call sound waves. Yes, the sound waves travel in the form of compressions and rarefactions. Instead of the tuning fork, if we take any other source of sound, say the speaker, then the sound waves generated by this object will also travel in the form of compressions and rarefactions. There is one interesting question. Is the sound wave a mechanical wave?
Yes,
Do you know what a mechanical wave is? The mechanical wave is a wave that requires some material medium to travel. And as we know, sound wave also requires some medium to travel. So yes, it is a mechanical wave. How do you define vacuum? Can sound travel through it? To find the answer to these questions, you have to wait for our next video. See you there.
can sound travel through vacuum? No, because it doesn't have any matter. That's why. Okay. So what I was going to explain to you is some terms associated with wave motion. So during wave motion, the particles of the medium oscillate, right? Oscillation or vibration. So particles of the medium undergo oscillation or vibration. What's the difference between oscillation and vibration? So first of all, let us understand what is oscillation. It is one complete, yes, to and fro or back and forth motion. Forward and backward. Again, it is also called one cycle. So called one wave cycle. So what's the difference between oscillation and vibration?
The time period
The time period. This can be called oscillation. It's a slow forward backward motion is a oscillation. Whereas vibration is very fast, like in machine,
So vibration is also like oscillation but much faster.
much faster. So it takes very little time to complete a cycle. Okay. So now let's define what is a time period. Capital T. Okay, before that, let's define what is amplitude. So during oscillation, what is happening? The particle of the medium is displaced from its main position or rest position. So maximum displacement from the main position. It is the maximum displacement from the main position. Of the particle. Of the particle of the medium. During wave motion. During wave motion is when the disturbance moves from one particle to other particle. So it is a displacement, so its unit will be what is the unit of displacement? Meter. Distance displacement. Unit is it is measured in meter. After amplitude, let us see what is time period. So it is the time taken to complete one oscillation or one vibration or one cycle. It is the time required for one oscillation. So what is the unit? Second. So whether it is longitudinal or transverse, both waves we can represent like this. Okay. For longitudinal, we will consider pressure and density. at the top. And at high pressure density, what is formed is compression. In transverse wave, the peak, this peak is not called compression, it is called crest. Okay, peak is called, so this is peak and this is valley. So valley is called in case of transverse wave as trough. Okay, so peak and valley are referred to as by different terms during transverse and longitudinal. Okay, then we have frequency. It is written as,
Oscillation intelligence.
yes, it is written like this. Curly V, it is read as nu. Nu. So it is the number of, it is the number of oscillations per second. Number of oscillations per unit time, which is 1 second. So how much is frequency? That is, frequency must be equal to 1 by T. Correct? T second for one oscillation. So 1 by T means number of oscillations in 1 second. T second correspond to one oscillation. Therefore, 1 second correspond to 1 by T oscillation. Okay, so that is frequency. So what is the unit of frequency? Unit is hertz or per second. Sometimes it is also referred to as cycles per second. CPS. How many wave cycles or oscillations per second? CPS. Okay, so it may be referred to as different. Then you have what is called as wavelength. So what is wavelength?
Outside.
Yes, is this chapter taught in your school?
No, but recently I had a discussion with my father on.
So wavelength, what is it? What is it? It is read as lambda. So wavelength is the distance traveled by the wave in one time period. Okay, like when the particle of the medium completes one vibration.
That is the time period of one vibration.
Distance traveled during one time period. So by the time the particle of the medium completes one vibration, the disturbance has traveled. Okay, so it is the distance traveled by the wave, the disturbance.
Which one also?
Oh, it is the distance traveled by the wave or disturbance in the medium. In one time period. Again, one time period or during one oscillation. Of the particle of the wind. So it's like this. So let's say we are looking at the motion of particle here. So when the particle does like this, that time the disturbance is traveled here. Okay, or during the transverse motion, the particle has gone here, here, and again here. That makes one cycle. That time the wave has traveled till here. That means it is already disturbing the particle which is placed here.
That is it.
This whole thing is wavelength. Wavelength is also the distance between two consecutive compression or two consecutive crests. It is also the distance between two consecutive troughs. Understood? So this also takes one time period. Is it clear? So this is also one wavelength from here to here. This will take how much? One time period.
Rest and rest fast.
Consecutive. Yes. So distance between two consecutive crests or two consecutive compression, or distance between two consecutive troughs or two consecutive rear crests. So, and the time taken to cover one wavelength is time period, because one oscillation will complete. Okay, so there are so many ways in which we can correlate. So now what is wave speed? Wave speed. So what is the unit of wavelength? That is simple.
I think it's A kind of.
Meter na yaar, it is.
No.
चाहिए ना न्यूमेरिकल कैसे सॉल्व करोगे
When you asked unit for that, I said B instead of.
that you have to ask yourself why are you answering like that. Now where is speed? Let's begin with unit now. What is the unit of speed?
Meter per second.
Yes. Okay. Now, so unit is meter per second. So what is wave speed now? Distance upon time. So obviously wave speed will be, we know the distance traveled is lambda, but time is time period. Right?
So the value of lambda will be given.
Yes, of course. So this is the disturbance, huh? Wave is disturbance. So we know when the wave travels distance lambda, the time taken is time period. Correct? So this is wave speed. And what is 1 upon time period? Frequency. So wave speed is 1 upon t is frequency, na? Okay. Can we define it?
Yes.
Okay. So both are the formula for wave speed. Okay. Since, why did we write this? Since speed is equal to distance upon time. The basic formula of speed. From this, in case of wave motion, we know when the distance is wavelength, the time taken is always the time period. And then, by the definition of frequency, these are the two formulas. Okay. So, what is the speed of sound wave? Speed of sound wave is it's about 346 meter per second at 25 degrees Celsius. So when the temperature of the medium is 25 degrees Celsius, this is the speed of sound in air.
Now this is fast. Now it is fast.
Yes, it will be more. So you have a table given. You can see speed of sound in different mediums. Page number 70. So speed of sound varies from medium to medium. It travels fastest in solid medium. Okay. And slowest in gaseous medium.
Because the distance between the particles goes to that.
So remind me, we will discuss the speed of sound in different mediums the next class. And after that, we'll discuss characteristics of sound. Or maybe we'll start with characteristics of sound then. Okay. So remind me in the next class. This is it. In this chapter, only concept to be understood is this. Once you understand that, rest is very easy.
Yeah, so that is just important because they get develop. So this is the time of you know getting this skill by like.
आप लोग एमबीबीएस में जाके बैठो